Hey guys, welcome back. I'm Dan Math. Today we'll be looking into parametric equations and vectors. Okay, parametric equations. So the typical set of parametric equations you'll see will be functions of time, where your parameter is t. So here is one. X equals t squared plus t, y equals 2t minus 1. Yeah, so when you're graphing these, something you want to do is make a table where you have t in one column and your x of t and y of t. That's just those. That makes it a lot easier to plot it and see the direction, because it's important to note the direction that the curve goes in, basically. Like, you're not always going to need that, but it's important to just keep at the back of your mind, you know. Another thing you need to know how to do is eliminate the parameter. In this case, it's pretty easy. We're just going to solve for t in the y equation because that's easy. And then we plug it into x, and we get this function. 1/4 y squared plus y plus 3/4 is equal to x, and so we know that is a sideways parabola. It opens to the right with a vertex at negative 1/4, comma negative 2. Which you can see right there. But our window is negative 1 to 1, so we don't have the whole thing. But yeah, that's the basic algebra of parametric equations. Okay, so we did algebra. Now on to the calculus part. Something that seems like we do a lot of in calculus is finding slopes of tangent lines, I guess. So we're going to want dy dx to find that. So we're gonna find any. This is the final equation, but we're gonna manipulate this, where x equals f of t and y equals g of t, and then we go through it, differentiate it. You get g prime of t equals f prime of little f of t times f prime of t. Then we have here solve for capital F prime of x, which is dy dx, and yeah, you get this. So that's really all you need to know, but that's very helpful when you're looking for slopes. Just a note, so you want your horizontal tangent line. If you want that, you need to make sure your dx dt is not 0, because then obviously it's undefined. Vertical tangent line, similar thing. We want it to be undefined, basically, so your dx dt has to be 0. Arc length of a segment. There's a whole derivation for this, but I don't think I have enough time to show it, the whole thing. So basically, this is the equation you need to know. Yeah, pretty simple, I think. Okay, vector valued functions. So we've got our generic vector. X of t, y of t, and z of t are your components. If you're in 3 dimensions, otherwise it'll just be x of t and y of t for 2 dimensions. Or you can write it like this, with your I hat, j hat, and k hat, which are your unit vectors. All they do is denote spatial direction. So I is x, j is y, k is z direction. What if you want to find the limit of a vector? Well, all you gotta do is go through each component and find the limit of each one separately, and you're good. So easy money, right? What if you want to find the derivative? Well, you just go through, same thing as the limit, and differentiate separately, and you're good to go. What if you want to find the integral, though? Well, it's the same thing. Just integrate each component, and you'll have the integral of the vector. Sometimes you'll have plus c if it's an indefinite integral, but yeah, so here's the plus c sign. Every time you're integrating indefinitely, just think of this and you'll never forget plus c. Alright, Dan Math is done. Now I'm going to have my associate Bahar go through some problems with you. Alright.
The first problem is asking us to graph a parametric function. This can be easily done by making a table of values with t, x, and y side by side. X and y give us the coordinates to plot on the graph, and t helps to show the direction of the curve as the function continues. For this particular function, the curve eventually moves to the right and gradually increases. Part A of the second problem asks us to eliminate the parameter and to find the curve's Cartesian equation, which gives the direct relationship of x and y. Here we can use x of t to rewrite t as a function of x. Then 1/4 times x minus 1 replaces t in the equation for y. This equation can then be further simplified to 3 cosine of 1/2 times x minus 1 plus sine of 1/8 times x minus 1. Part B asks us to do the same thing. Once again, we rewrite the function of x. Note that the function that is easiest converted should be used, and it isn't always x of t. Here x of t becomes t equals 1/4 times ln of x plus 1, which we then can plug into our equation for y. After expanding the equation, we can simplify it. Our final answer becomes 1/16 times ln of x squared minus 1/4 times ln of x plus 3. For problem 4a, we're given the derivative of a vector function. I've rewritten the vector without unit vector notation, where I, j, and k describe the x, y, and z axis. We're looking for r of 8, so we need to integrate the derivative that we've been given. With vectors, you can integrate each component separately. Do not forget the plus c. Using r of 1, we then solve for the values of c. C is a different value for each component in the vector. After adding them to the general equation for r, we can plug in 8 for t and get our final answer. In problem 4b, we need to derive our original vector. Like integration, derivation for vectors is separate for each component. Once you find the general equation for the second derivative of r, plug in 1. This gives us the values 0, -5, and -2. Finally, problem 4c requires that we find the arc length of the curve from t equals 1 to t equals 4. Here's the general equation for arc length. In problems for particle movement, this equation represents the distance traveled, or the equation for speed integrated. We already know dx over dt, dy over dt, and dz over dt from our original vector since it's the derivative. Applying the components to the equation, the calculator gives us the answer of 41.328.